Greetings, this is Capstone Group 67, and the topic of our Capstone project is design of FPGA-based quadcopter. The main goal of our project is to design a flight controller on an FPGA using a hardware description language. Now, we have been pursuing this project under the guidance of Dr. Manu Bansal and Dr. Anil Singh. Now, on to the members.
I'm Raghav Jain, and I am a student of Electronics and Communication Engineering.
My name is Kunal Badgali, and I'm a student of Electronics and Communication Engineering.
My name is Shubham Mittal. I am a student of Electronics and Communication Engineering.
I'm Priyanshu Kumar and I'm a student of Electronics and Communication Engineering.
I am MSSS Aditya and I am a student of Electronics and Communication Engineering. Now we start with the hardware setup of our quadcopter. First we have a frame and a support for the frame which is used to prevent the components in cases of crash landing. Then we have the motors. These are A2212 brushless motor DC motors with a rating of 1400 kilovolt. Then we move to the ESCs. These are electronic speed controllers that can drive the motors that have a current consumption of up to 30 ampere. Then the propellers. These propellers along with the motors are used to generate a thrust which helps us in lifting our quadcopter from the ground. Next we have the receiver. This is a 2.4 gigahertz receiver that is used to receive PWM values which are transmitted from the transmitter, which is an FlySky C6 transmitter. Then we have our sensor. This is the MPU 6050 gyroscope and accelerometer sensor. It is a 6-axis motion tracking device for which has 3-axis accelerometer and a 3-axis gyroscope. So we'll be using the 3-axis gyroscope in our project. Then we move to the FPGA. This is a Basis 3 board from Digilent. It has an Arctic 7 FPGA. So this FPGA has several input and output pins. Now we are using these input pins to receive the values from the transmitter via the receiver, and then we also take as input the values from the sensor, the MPU 6050 gyroscope, and then we calculate the required response to the given inputs, and the values from the FPGA, the calculated output, are fed back to the electronic speed controllers in form of pulse width modulated waves. These pulse width modulated waves, based upon the duty cycle, drive the motors at the required speeds. Now to power our setup, we have a 2200 milliampere hour battery, lithium polymer battery. The main purpose of our project was to design the flight controller, which will be explained by us further. Now we come to the flow diagram of the flight controller. So first we have the I2C master and the MPU driver. These are modules embedded on the FPGA. So the I2C master and the MPU driver are used to get values from the MPU 6050 sensor, and these values are further transferred via a low pass filter into the main control unit. While on the other side we have an RC receiver receiving the values from the transmitter, which are further passed into the decoder. The decoder is a PWM decoder which decodes the PWM signal to get the duty cycle of the input wave. Now this is passed on into the main control unit again. The main control unit contains the PID algorithm, which is responsible for to calculate the response of the motors, the required response. It takes in the values of the sensor as well as the decoder. The 3 response values are then added together to a motor mixing scheme that will stabilize the quadcopter. Now after calculating these PWM signals, we further feed them into the PWM encoder. The PWM encoder calculates the signals and feeds them to the motors, the ESCs. This is the component flow of the same.
The first module of a flight controller. This is the PWM decoder. The main objective of this module is to obtain the PWM signal from the transmitter via the receiver. So this is the receiver and it has 6 channels. Each of the channel outputs a PWM signal, which is a pulse width modulated signal. Here we can see the actual outputs of the receiver that we have observed on a digital storage oscilloscope. And this output is then processed by the module and converted into a format which is as follows. So here we can see that when we push the stick up or down, the PWM signal that has been transmitted is displayed on the 7-segment display of the FPGA. Here the pulse width is being displayed in microseconds divided by 10. So 190 corresponds to 1900 microseconds. And PWM encoder, the main objective of this module is to encode the output signal in a PWM format, and it helps us to control the speeds of each of the motors by varying the duty cycle of the signal. Now in an electronic speed controller, it works on 50 Hertz and the input signal has to have on times of 1 to 2 milliseconds. Here,
LPF, that is low pass filter. The output from the MPU 6050 sensor contains some noise. Therefore, to filter out that signal, LPF is used. The filtered output is sent to the main controlling unit. Here you can see that this is the input which contains some noise, and this is a filtered output that will be sent to the main controlling unit.
Next part is I2C communication, and it contains 2 modules, I2C master and MPU driver. I2C master is a generic inter-integrated circuit communication master used to read and write data from or to the MPU6050 sensor. It controls two communication line, STL and SCL, to get data from the sensor. To control I2C master, we use MPU driver module. MPU driver is used to provide commands to the I2C master. It controls the states of I2C master through command signal. It sends the acquired data from gyroscope sensor to main control unit to apply PID algorithms on it. So as shown in the video, we are seeing the 16-bit output of each axis from gyroscope sensor. 8-bit of which are MSB and 8-bit are shown on the 7-bit segment display. We can control X, Y, and Z axis by 2 pins on the bottom right corner, in which 00 corresponds to X axis, 01 corresponds to Y axis, and 10 corresponds to Z axis.
Now let's move on to the PID controller. We are going to be using a discretized version of a PID controller. Here we can see that we are going to give an error signal and we are going to get a controlled output from the other end. There will be 3 intermediate signals that will be produced, that are the proportional signal, integral signal, and differential signal, which will be given by these particular formulas. Now in this particular graph, we can see that we have taken a sample set of gyroscope values, which we have taken from MATLAB and Arduino. And this sample set of gyroscopic values are given as input to our PID controller, which will be acting as our error signals. As we can see that in the input signal, there are a lot of variations, lot of changes, as what we had hoped, so as to get a clear picture of whether or not a PID will be working properly. And as we can see, the variations and the errors are minimized, and we can see that the spikes and the errors have been lowered as we increase the gain. We can see that the value is much more settled around one particular region as compared to the input. This particular project has a lot of future scope, as a lot of different things can be integrated into an FPGA. We would like as many suggestions as possible on this particular project.